Hello everybody, I am Reeti Mukherjee, faculty at Department of Mechanical Engineering, and welcome to the first live session for the subject Kinematics of Machinery. Here I will be discussing few of the very important topics from Unit 1, Machines and Mechanisms. So what do you think of when you hear the word machine? Obviously, when you think of machine, you must be thinking of a very simple thing like a pulley or a wedges, screws. They are also not just elements, but the machines which make our work simple. So now you can also think of the higher level machines like automobiles or air conditioners, etc. Yes, they also fall under machines. So let us now see in detail what exactly is a machine. See, the definition says the simple machine is nothing but a mechanical device that changes the direction of or the magnitude of a force. In general, they can be defined as simplest mechanisms that use mechanical efficiency to multiply the force. Let us see some of the examples. As I told you, the lever, wheel and axle, the pulley, inclined plane, wedge and the screw. In each of them, you can see the work is done only by applying very little amount of force. So it is making our work simple. So that is the purpose of a machine. So let us now see what is actually a mechanism. A mechanism is the one which consists of a number of parts. Technically saying, number of parts in the sense number of elements. See, for example, this is an arrangement you find in automobiles wherein you can see the crankshaft. These are number of elements, number of parts that is giving some kind of work output. This is nothing but the crankshaft on which you have connecting rod, piston pin and the piston. There are four different elements mounted and gives certain work output. So this is making our work simple. This is just one of the mechanisms finally constituting to give us a larger output, giving us machine. So I'll say that number of elements make a mechanism, number of mechanisms constitute to give a machine. So see, each part of the machine which moves relative to each other, they are called as link. Now, link and element both are same. Link is nothing but one of the smallest unit of a mechanism. Now, what is mechanism? That is again a smallest unit of a machine. I'm saying in other words, link makes mechanisms, mechanisms make machines. See, here you can see a word called relative. See this word called relative. Now what do you mean by relative? Suppose I am traveling in a bus. If somebody is asking me whether you are moving, are you in motion or not? I would say that question is completely incomplete. You must be asking me whether I am in motion with relative to something. See, if I am traveling with somebody, my co-passenger, with relation to that co-passenger, of course I am not in motion, because both of us are traveling. Now, if with relative to the tree that is standing outside the bus, of course I am in motion. So that is nothing but relative to the other part. So I am saying that the link is nothing but the part of a machine which is having relative motion with each other. Similarly, I also mentioned that mechanisms are made of links. Mechanisms make machine. Here, for example, you can see this is a single rigid body. When two rigid bodies are paired up, you see mechanical linkage is formed over there. Now, let us talk about classification of links. How many types are the links classified? First one of which is a rigid link. Rigid in the name itself says it is a resistant body. What is meant by resistant body? It is taking up the force and not undergoing any kind of deformation. So it means it is not changing its shape, in other words. So say rigid link is nothing but the link which is taking up the load and not undergoing any kind of deformation over a long period of time. For example, you have a connecting rod. So these kind of connecting rods are found in automobiles. Just before I gave an example, this kind of connecting rods, even after prolonged loading over a long period of time, does not undergo any deformation. Okay, let us say this is an ideal case. Actually, no objects are there which will not undergo any deformation. Only minute deformation takes place in connecting rod over a very long period of time. Next one comes flexible link. In the name itself says flexible link. That means it will undergo some deformation. For example, you have springs, belts and ropes, chains. So I mean to say that fluid flexible link is nothing but the type of link which undergo deformation over a period of time on being loaded. So these are some of the examples. This is the spring and that is the belt and rope arrangement. Last one is the fluid link. You must be thinking fluid link cannot be fluid. Of course, links are not fluid here. I mean that the links are not directly connected here, but the pressure or the force that is transmitted to one link is transmitted to the other link using a fluid medium. For example, I'll give you a hydraulic press here. Here you can see there is a hydraulic fluid Hello. Okay, sorry for the interruptions. Let us continue with the sliding pair. As I was saying, when you talk about sliding pair, you imagine a surface contact. So here you can see that there is a rectangular slot here, and there is a rectangular block which is having a sliding motion. It cannot be turned. It has only one definite path, that is sliding in this direction. So this is nothing but sliding pair. For example, in our let's say day-to-day life, we see sliding windows. So they can be considered as one of the examples where we see sliding pairs. Next comes turning pairs. Here you can see there is a bearing and there is a shaft, crankshaft, which is having a rotatory motion. It can be sliding also, but now we are considering turning pair, so I'm giving you the example of the shaft that is turning inside the bearing wall. The collar is there. So here, the one of the link is turning over the other. This comes under the example of turning pair. Come to, again, the day-to-day life example I can give. You have seen a door, right? When you open and close the door, you see hinges. The doors are connected with the help of a hinges. So hinges are one of the examples of turning pairs. Here you see the roller bearing. This is one of the example of rolling pair in which the bearings are rolling over one another. The casing. This is the casing. These are the rollers. The rollers are rolling in between two casing, the inside case and the outside case. So in this, one of the link is rolling between two casing. So this is a roller bearing. What is the use of a roller bearing? It reduces the friction between two mating parts. For example, if it is mounted on a shaft, and on the shaft if you mount a pulley, if you want to take a, let's say, belt over the pulley, so the mating parts are the pulley and the shaft, it will reduce the friction between the shaft and the pulley. That is the function of a roller bearing. Now this comes with spherical pair. So spherical pair, you can see there's a casing, fixed element, and there's a sphere in here. So see, this is the casing and this is the, let's say, the sphere. Scaring and this is the casing and this is the sphere. So if you have to rotate this sphere in between a fixed element, that kind of pair is nothing but comes under spherical pair. So where can you see, have you ever seen this kind of arrangement? Actually, we have seen in our day-to-day life when we drive two-wheelers or the three-wheelers. Can you relate one of them to this? See, I say this is the arrangement where we find whenever we have the attachment of our rear view mirrors in our automobiles. Let us say I drive a scooty. So in that scooty, when I try to attach the mirror, there is this kind of arrangement I find. This is a screw pair where you can see two links are there and in which one of the links are turning about the other element with the help of screws. So in the name itself saying screw, so take a simple example of a screw. If I want to nail a screw inside the wall, how do I do it? I turn the screw, even if I'm turning it, it goes in a linear direction. For example, even simpler example if I give, let us take a bottle. So bottle neck has a threading. You turn the cap of the bottle round and round, but the cap goes in a linear direction. So that kind of threading, if you see anywhere, you can see they are a screw pair. Next comes the classification of kinematic pairs according to the nature of contact. See, you will find there are two types. One is the lower pair and the other was the higher pair. Lower pair is the one where you see there is a surface contact between the links. Again, the same examples come into picture. You have screw pair and the spherical pair, they come under lower pair. Next are the higher pairs. So in the higher pair of kinematic pairs, you have point contact. Suppose you are rolling a ball on the surface. So if you are rolling a ball on the surface, you will have only a tangential point of contact throughout. Not the whole surface of the ball will touch the ground, but only a point contact will be maintained. So such kind of examples you can see in gears and belt and pulley. Next comes, whenever you want to talk about the nature of mechanical constraints between the links, there are again two types of kinematic pairs. The one is self-closed pairs, the other is force-closed pair. When you talk about self-closed pair, you see two elements are connected together mechanically, and only if I destruct one of the element, then only they can be broken, the contact can be broken. The contact between two links only will be broken if and only if I break one of the element. So this is where you see the screw. If I nail the screw, either I have to break it, or if I see this spherical pair example also, the mirror I was talking about, if I even have to break the link, I have to destroy one of the links. See, I also, as I have seen in the examples pictures here, all the lower pairs and some of the higher pairs come under the self-closed pairs. Now, force-closed pairs. Here there is a beautiful example of cam and a follower. Let me just tell you briefly what is a cam and a follower. So, cam is nothing but an element which is rotating with this kind of profile, and follower, as the name suggests, it follows the cam profile, and cam is rotating, the follower is reciprocating. This kind of arrangement also is found in automobiles. Here you can see an element called spring. So this spring, function of this spring is to hold the follower. So this kind of arrangement we see it will be helpful in giving an example of force close, where two of the links are not mechanically connected. With the help of the spring only, the follower is connected to the cam. What will happen if I remove the spring? The follower will not hold up. So this is one of the example of force close, where two of the links are not mechanically connected, but they are held together with help of some other mechanical element. Here we say it is a spring. Let us now talk about kinematic chain. How did this kinematic chain come into picture? Till now we have been talking about pairs. Pair means only two links. So when I say two links, what will happen if more number of links are attached? Let us say 2, 3, 4. So let us say they will form a series or a loop or a chain. So here came the idea of kinematic chain. So kinematic chain are nothing but when the kinematic pairs are coupled in such a way that the last link and the first link are joined together. You see simple chain that you wear. In that also the last link and the first links are joined together. Only then you can form a loop. So those kind of chains are nothing but kinematic chains. Here you also have certain relations between number of links and number of pairs, also number of joints and number of links. So here we see this L says number of links. Now what is P? Number of pairs. What is J? Number of joints. Again, L is number of links. Here you will be seeing LHS, RHS terms are used. Here I am using this equation and they are saying that the chain is logged. Let us now try ourselves. I am saying L is equal to 2P minus 4. So let us take an example of number of links. Let us take it as triangle. This is one link. This is another link. This is another link. This is one joint. This is one joint. This is one joint, this is one joint, and this is one joint. So how many number of links are there? I can say L is equal to 3. Now what is this pairs? Pairs are nothing but, I told you, kinematic pairs are 2 in number, 2 taken at once. So this is, let us say, L1, this is L2, and this is L3. So L1 and L2 form one pair. So L1, L2 is one pair, L2, L3 another pair, L3, L1 again one pair. So number of pairs is nothing but 3 again. If I substitute the same thing in this equation, what will happen? 3 is equal to 2 into P, that is 2 into 3 again, minus 4, which will give 3 is equal to 6 minus 4, which is 3, here it is 2, but 3 is greater than 2. 3 is greater than 2, which satisfies the first equation. If LHS is greater than RHS, then what is happening? Chain is locked. Obviously, you can see that 3 links are very much locked to each other. They cannot transmit any kind of motion to the other part. There is no particular relative motion in between them. This comes under chain, locked chain. Now let us consider, we have the equation, say L is equal to 2P minus 4. What will happen if I take L is equal to 4? Till now we have been taking that L is equal to 3. Now let us take L is equal to 4. What will happen? So say L is equal to 4 means we will get an let's say chain like this. This is one link. This is another link. This is another link. This is another link. So these are the number of joints. So this is L1, L2, L3 and L4. This is the number of 4 links are there. So here we will say L is equal to 4 again. And how many pairs are there? P is equal to, again N1 and L2 form one pair, L2, L3. Okay. So L1, L2, L3, L4. So L1, L2 form one pair, L2, L3 another pair, L3, L4 one pair, L4 and L1 again another pair. So number of pairs is equal to how much? 4 again. L is equal to 4, P is equal to 4. Substituting the same thing in this equation, that is L is equal to 2P minus 4, we get 4 is equal to 2 into 4 minus 4 again. So which gives 4 is equal to 8 minus 4. Of course, 4 is equal to 4 here. So when you have the RHS is equal to LHS, that means this particular 4 bar, let's say chain, 4 link chain will be giving you constrained motion. Same thing we have seen here also. See, when LHS is equal to RHS, then the chain is constrained. Now coming to the constrained part, what do you mean by actually constrained? So this constrained meaning, literal meaning is when you have let's say a chain or a links moving in only one definite path, that is coming under constrained motion. Okay, so let's see the third part also. Shall we check? If you have LHS is less than RHS, then the chain is unconstrained. So let us say if I take number of links as 2, you will see that LHS will fall under less than RHS condition, which will be of course unconstrained. Unconstrained again, it will not have any definite path. It can move in a number of directions. So that is the meaning of unconstrained motion. So here today we will be discussing, this is the most important part of the chapter. The most important kinematic chains are these three: 4-bar chain, single slider crank chain, double slider crank chain. Now, what are these 4-bar chain? 4-bar means there are 4 links in that. Single slider crank chain, that means there is a single slider. The slider element is introduced in this. Third one is double slider crank chain. In the third one, there are double sliders. That means 2 sliders are introduced in this. Now, previous slide, I said these are the number of links. These are the number of links. These are the number of links. If there are 4 links, I said they fall under constrained type of chain. Now, what will happen if I fix one of them? Or let's say, before it was having random motion. Now, if I fix it, any given input will give certain definite output. Yes or no? So, if I give definite input, definite output is obtained. So, such kind of thing gave us an idea of fixing one of the links in a chain. That changed these chains into mechanisms. So, I say when one of the links of a kinematic chain is fixed, they are named as mechanisms. Okay? So, now this 4-bar chain becomes 4-bar mechanisms. Single slider crank chain became single slider crank mechanism. Double slider crank chain became double slider crank mechanism. Let us study each one of them separately. See, this is how your 4-bar mechanism look like. See, here you have this link as fixed. This is this link L1. This is, let's say, L2. This is L3. This is L4. This particular link is fixed. So that particular link is not moving. Can you see? This is not moving. One of the link is completely rotating one whole path. See, if I draw. See, it is traveling in a one whole complete revolution. The other one is only oscillating. Path of oscillation is given for that particular joint. So see, this is a fixed frame. This is the link that is completing one whole revolution. The other one is just oscillating, and the one in between is connecting the crank and the rocker. So in order to form such kind of mechanism, the perfect 4-bar mechanism, there is a rule given. That is nothing but the Grashoff's rule. What does the Grashoff's rule say? They say that the sum of the lengths of the smallest link and the largest link should not be greater than the sum of the lengths of the remaining 2 links. So let us say, I will draw here one 4-bar mechanism. Let us say this is link 1, link 2, link 3 and link 4. It is very obvious that L2 is the smallest one, L4 is the largest one. So I mean to say that L2 plus L4 should not be greater than the sum of the lengths of other two, L3 plus L1. Simple, the statement is converted like this. The sum of the lengths of the smallest link and the largest link should not be greater than the sum of the lengths of the other 2 links. So this is coming under the Grashoff's rule. So one 4-bar mechanism has to first of all satisfy this rule. Only after then we can alter with any of this lengths. Now we have a nomenclature following this different kind of links. So I told you the one which is fixed, the one which is completing one whole revolution, the other one is just oscillating, and the one which is connecting the crank and the the rocker. So we say that the one which is completing one whole revolution is the crank. The crank is rotating and completing one whole revolution. The one which is fixed here is called as frame. Now the one, can you see there as only oscillating? That oscillating link is called as a rocker. Is called as connecting rod. Okay, so there are four. These are very important. You must be remembering this, because when we solve problems, they will not give any link, but they will specify as a crank, frame, etc. So these terms are very, very important. The crank is nothing but, again let us repeat, the crank is the one which is rotating and completing one whole revolution. The frame is the fixed link. The rocker is the one which is oscillating only, and the intermediate link which is connecting the crank and the rocker is known as connecting rod. Now see, if you see here, this is the path obtained by this particular mechanism when I fix this particular link. Do you think it will give the same path if I fix this L2? Or come back here, let us say I have fixed this L1. So now the behavior of this mechanism will be a certain type. Now if I, let us say, erase this and I say that I am going to fix this particular link. It is still a 4-bar mechanism, but will this mechanism be similar to the previous one? Or let us say, no, I will not fix this one, but the third link, this one. Now will this one be similar to the first one and the second one? Now if I say no, I will not even fix that one, I will fix the fourth one. Now behavior of all these 4 different kind of link fixation, will that give the same behavior? Of course not. So they have come up with the idea of changing the fixation of each links and obtaining different number of mechanisms. That particular thing comes under the topic called inversion of a mechanism. This is there for 4-bar mechanism, single slider crank mechanism, double slider crank mechanism. So first of all, let us see how the behavior of fixation of each links are shown in a 4-bar mechanism now. So what is the inversion again? Inversion is nothing but it is obtaining more number of mechanisms by fixing kinematics links, by fixing each number of kinematic links one at one time. Okay, so let us say here link 1 is fixed. So you obtain one crank is there and one is oscillating. The same example that I have given for a 4-bar mechanism. See here L1 is only, L2, L3 and L4. So L1 is fixed, frame, L2 is completing one whole revolution, so crank, L3 is connecting the crank and the rocker, so connecting rod, and L4 is called as the rocker. Why it is called as a rocker? It is because it is only oscillating. You have seen the baby rockers, right? They only oscillate. So that is how it has got its name as rocker. Now coming to the second part, see, you have seen the first link is gone, the second link, L2 here also, L4. So here instead of L1, L2 is fixed. See, did you observe any change in the behavior of this or path of this mechanisms? See, here you are obtaining 2 cranks. 2 links are completing one whole revolutions. So this is called as double crank. Double crank mechanism. Because there are 2 cranks. So double crank mechanism. Next, let us see this diagram. Here you see, this is again L1, L2, L3 and L4. So instead of L1 and L2, here they are fixing the link 3. So link 3, if it is fixed, again this is also obtaining one crank and one oscillation. Though you may think that this mechanism and this mechanism are same, they are not same but similar, but the path obtained here is upside and here it is downwards. So they are again considered to be two different mechanisms. Here also, instead of L1, L2, L3, if L4 is fixed, you see both the links are only oscillating. So this is called as rocker-rocker mechanism. Okay, this is crank and rocker mechanism. This is also crank and rocker mechanism. See, crank and rocker. Rocker and levers are same. So these are some of the examples, applications, examples of crank and lever mechanisms. Here, you can see. This is double crank mechanism. You can see two cranks are there. This is used in, you see, automobiles. The locomotives are there. The wheels of the locomotives, you can see, both are rotating like this. You must be seeing that in trains also, locomotives. In that also, you can see the wheels arrangement. That thing is the basic application of this double crank mechanism. Next comes single slider crank mechanism. Let us see what is a single slider crank mechanism. Till now we have been seeing 4 bars where there are 4 bar mechanism. Now one of the bar, if I replace that with one of the slider element, the same mechanism turns out to be single slider crank mechanism. See, you can see single slider, a single slider and one crank. One slider is there and one crank is there. See, this is the crank path. So this particular link is completing one whole revolution. So this is called as crank. See, it is named as crank. This is the connecting rod. This is the slider, and this particular thing is fixed. So that is called as a frame. Okay. So see, here if I want to find out, let us say, okay. So here we are talking about the number of turning pairs and the sliding pairs. Here we have seen what are the number of pairs that is forming a turning pair. There are 3 in number. Sliding pairs, the link 4 was only sliding over link 1. So that is considered to be 1 sliding pair. See, the inversions here now. How many number of elements are there? 4. How many inversions are possible? 4. Why? Because we are fixing each link at one time. So first inversion, first link fixed. Second inversion, second link fixed. Third inversion, third link fixed. And the fourth element slider, if that is fixed, fourth inversions is possible. So let us say first inversion. See, here link 1 is fixed, very much clear with the diagram. Here see, link 1 is fixed. 2 is turning over this one link. So see, this is arrangement that we find in a piston and cylinder arrangement. Second inversion where link 2 is fixed. Can you see here link 2 is fixed? So if link 2 is fixed and as the output I attach a tool at the other end, you see that slider will yield a horizontal motion. So that slider is connected to a cutting tool. If that cutting tool I measure from E1 to E2, that is the stroke length, if I see that, they say that when it is moving forward, it is a cutting stroke, and when it is returning back, it is an ideal stroke. That means there is no cutting happening there. So see, E1 to E2 is the stroke length, and when it is moving forward, see here, when D is giving to E1 and E1 is moving to E2, it is going to cut the metal or the workpiece, and when it is returning back, that means here, it is again going to return back, and it is not going to give any cutting, it is only a ideal stroke. Here you can say alpha and beta, they are the angles here. There is a term called quick return ratio that comes under picture when you talk about the alpha and beta, that comes into picture. The third inversion is saying when link 3 is fixed, very much evident over here. See, link 3 is made to be fixed here. There is a slot here, slotted lever is given, in which the slider is moving, also making a complete revolution. Here also, when it is attached to a tool here, this tool is going to travel from one end to the other, let us say from here to here. This is going to give you stroke length, and that also is again going to give you a cutting stroke in the forward direction, and backward direction is going to give you the ideal stroke. You can see the fourth inversion. Fourth inversion is where you have the slider as fixed. It is used in hand pumps. Hand pumps. The slider is fixed here, very much evident in the diagram itself. The fourth inversion where fourth link or the element is fixed. Here this double slider crank mechanism, this is how it looks. There are two sliders, let us say S1 and S2. Again, link 1 is the frame here. Then link 2 is this slider. Link 4 is this slider. Link 3 is the connecting rod, which is connecting this slider and this slider. Okay? So first inversion is where the total frame is fixed. See, the total frame, instead of drawing, they have just given like this. The total frame is actually fixed. So when it is totally fixed, the practical application is seen in elliptical trammels. Now what is elliptical trammel? The elliptical trammel is a device which is used to obtain a perfect ellipse. Now how to show that if it is giving a perfect ellipse or not? Let us convert that into mathematical terms. Let us say it is making some angle theta here, since it is parallel lines. So I can say if this is theta, this is also theta. And the distance, let us say take it is x here and y here. If I convert that into mathematical terms, if I want to write x from this particular triangle, it will say this is cos, trigonometric ratios if you are clear with, you will see that if I want to write x here, it will be BC cos theta, correct? Now if I want to write y, total distance y, I have to consider this big triangle, and still y will be AC sin theta. So if I write cos theta from this, let us say this is first equation, this is the second equation. So cos theta is equal to x by BC, and sin theta is equal to y by AC. We know that cos square theta plus sin square theta, if I square them and add them, what will happen? We know that this particular term gives 1, and cos square theta will be x square by BC square plus sin square will be y square by AC square is equal to 1. So this particular expression is similar to the ellipse equation where it says x square by a square plus y square by b square is equal to 1. That is the equation given for ellipses. So here hence proved that yes, this particular arrangement of the links will finally yield a perfect ellipse. This is how it is proved. This is one of the very important aspect or topic that is asked in the exams also. Second inversion of this double slider crank mechanism is this one, where the second link or this particular link which is connecting rod is fixed here. So you can see that it is giving a rotatory motion. This particular arrangement is used in Scotch yoke mechanism where a rotatory motion is transmitted from rotation to linear transmission, linear motion. So rotatory to linear or reciprocating. Linear motion. So slider is going to slide in a linear motion and this particular link is going to rotate in rotation direction. Rotation. So third inversion is a very good example. Here I have taken as Oldham's coupling. So coupling, what is the basic use of a coupling? Is nothing but joining or uniting two mating parts. Two parts basically, not mating parts but two parts. If you have to join them together, you have to use a coupler. So Oldham's coupling has a speciality. It joins two parallel shafts with a very short distance between. Axial distance should be very short. So here you can see this axis and this axis, there is a difference. Short distance, of course. So here you can see there are a number of links, link 1, link 2, link 3 and link 4. The link 1 is the intermediate piece. This one is the link 1. Link 1. Then link 2 is the opposite shaft. This is the link 2 here. If you see the view like this, if you want to explode and see the view, they are the ones. Link 1, link 2, link 3 and link 4 are there. So distance between two shafts. This is the driving shaft, this is the driven shaft. The two shafts, the parallel axis is different. The axial difference between those should be short. Only then the application of this can be seen. Now, when you learn about a machine or a mechanism, you always want to know how long or what is the longevity of that particular machine or how long will that work. What is the efficiency? How efficiently is going to work? Here in technical language or like in this language, if you want to give the efficiency of a machine or a mechanism, they talk about in terms of mechanical advantage. How advantageous is that machine? Mechanical advantage of that particular machine. So in terms of mechanical advantage is given as the ratio of output torque to the input torque. So I'm saying that mechanical advantage is given as the force output by force input. If you further give it in a derivation form, you will find that it is a ratio of output torque exerted by the driven link to the required input torque at the driver link. Okay, so there's an important point to this also. Let us talk about that now. See, here you can see a different angle of this. This is the fixed link, of course, link 1, link 2, link 3 and link 4. Here can you see alpha and beta also? So what are these alpha and beta? We say that the mechanical advantage is directly proportional to sine beta and the angle between the coupler and the driven link. It is also inversely proportional to the sine alpha, the angle between the driver link and the coupler. This is the driver link because this is where the input is given, driver link. This is the driven link. The output is obtained at the driven link. So that is nothing but this is nothing but the connecting rod. So here how your sine beta and sine alpha, the relation of that is given. So these angles are not actually constant because they are constantly moving. So hence mechanical advantage also is not actually constant, it is continuously changing. See, if this alpha position, if alpha is becoming 0 or 180 degrees, what will happen if this is, see here there was a link, if alpha is becoming 0, this is how it will look. If this is the condition, it will have mechanical advantages infinite. So these kind of positions are called as toggle positions. So these particular positions are called as toggle positions. And the angle beta, what is the name given to this angle beta? This angle beta is called as the transmission angle. See here your alpha is becoming 0, here alpha is 180. So now let us come back to the summary of this whole session. So we have started with what is a machine, and we have seen that how machine is made up of number of mechanisms. And what are the mechanisms consisting of? Mechanisms are again consisting of number of links or elements. They let's say coordinate with each other or have the relative motion between each other. And then finally give certain mechanism. These certain mechanism, number of mechanisms constitute together to give a machine. That is how we have learned about machine. Now how these links are classified? We have seen rigid link, flexible link, fluid link, and what are the examples? We have seen all of them. Now coming to the pairs, kinematic pairs, we have seen that each link individually, then how two links are joined together and form a kinematic pair, then how more number of, let's say more than two number of pairs, if they are joined together, how they are forming a kinematic chain. Types and classification of chains also we have seen, according to the nature of contact, according to the relative motion between them, according to the mechanical constraints between them, like sliding pair, turning pair, rolling pair, spherical pair, and then screw pair, lower pair, higher pair, all of the different examples, let's say forced closed pair, self-closed pair. We have seen number of beautiful examples of them. I hope the examples are very much relative because I have tried and chosen day-to-day life examples so that it doesn't complicate this topic. Then later we have seen how a kinematic chain is formed where first link is joined to the last link, and then different types of kinematic chains like 4-bar chain, single slider crank chain, double slider crank chain. Then we have also seen how a chain is let's say having a random motion and what to do in order to get a definite motion. What we have done is we have fixed one of the links and yielded a mechanism. And how a 4-bar chain is converted from 4-bar chain to a 4-bar mechanism, single slider crank chain to a single slider crank mechanism, double slider crank chain to a double slider crank mechanism. We have also seen their inversions. In order to obtain different number of mechanisms, we have fixed each link at once, one at a time, and obtained number of mechanisms. We have also seen the examples of them, and then finally obtained the efficiency of the mechanical machines also. We have seen how the toggle positions are obtained and what is the transmission angle. So this is a few of the very important topics from Unit 1. Let us see. Hope you have all you've all received very nice, let's say some benefit out of the session. I hope you all do very good out of them. Thank you. Okay, so we have got somebody commented on this one, as in why we have got BS cos theta and sin theta when we are talking about x and y. Because see here we are talking about getting a mathematical expression out of this particular link arrangement. See here you have taken a theta, and when you talk about trigonometric ratios, this is the adjacent angle, this is the adjacent side, this is the opposite side, this is the hypotenuse. So when you say cos theta, if I want to write, let us say O here, I am just giving an example. If I say O here and I want to write, let us say cos theta, cos theta. So that will give, what is the formula for cos theta? Cos theta says it is the adjacent side by the hypotenuse. So the adjacent side is OB by BC. So OB is nothing but what? X. So I'm saying cos theta is equal to X by BC. That is nothing but cos theta. So that is how cos theta is obtained as X by BC. Also similar way, if I take the bigger triangle here, say here also I put P. If I want to write sine theta out of this big triangle ACP, what will happen? Sine theta means opposite side by hypotenuse. So opposite side means what? This particular thing, CP. But hypotenuse is what? AC. So sine theta is CP means again what? CP is equal to Y by AC. So same thing has come here. Sine theta is equal to Y by AC. That is how you have got sine theta and cos theta of the first inversion. Thank you.